Hi, everyone. My name is Sergey Smirnov. I'm a senior technical specialist in Microsoft and Cosmos Global Blackball team. And today we're going to talk about graph analytical use cases, which can be solved with Azure Cosmos Gremlin API and Azure Synapse using Spark Graph Frames library. So this is our agenda for today. We're going to look into Azure Cosmos DB and Gremlin API. We're going to talk about transactional OLTP graphs versus analytical OLAP graphs use cases and how they're different from each other and the challenges as well. Then we're going to quickly do a sneak peek in Azure Cosmos DB Analytical Store Synapse link because we're going to use a portion of this in my demo later on. And essentially, we're going to talk about the Gremlin API Spark integration, how it's used, and how we can use it to solve analytical OLAP graph use cases. And we're going to wrap up everything with a demo walkthrough of using Spark Graph Frames library from Synapse Spark to explore graph analytical use cases on top of Cosmos DB Gremlin API data. So first in Azure Cosmos DB. This is a NoSQL database which is positioned for modern applications, which has SLA back speed availability, automatic instance scalability, and multiple open source APIs for different NoSQL patterns. We guarantee new speed at any scale. We simplify application development with multiple SDKs for your schemaless data. We are mission critical ready. We guarantee you business continuity with zero replication, 5 nines availability, enterprise level security, and we are fully managed and cost effective. We give you that different modes of provisioning with serverless and automatic scaling to match your application needs. What is Cosmos DB undercover? We have different APIs for different use cases. Table for key value store, Cassandra for column family, Core SQL API and Mongo API with document database, and we have Graph API for Gremlin API for graph use cases. All those APIs are served undercover by Azure Cosmos DB platform, and they all have the same guarantees of global distribution, elastic scale out, same low latency guarantees, and same SLAs. But today we're going to focus on Gremlin API. So if we zoom into architecture of Cosmos DB Gremlin API, currently it is using the Azure Cosmos DB partition storage, basically horizontally partitioned storage based on the partition key, the hashing shards to do the read-write operation from your graph database engine, which has a wire protocol support with Gremlin API based on your open source Gremlin SDKs, which is used by application. Now, what does Cosmos DB Gremlin API good at? It's good at elastic scalable storage and throughput for graph data and operations. It's good at high throughput for reads and writes. It's good at high concurrent transactional workloads, meaning that from Gremlin perspective, you can easily create high volume vertices and edges in your graph database. It is a fully managed platforms, so you don't have the complexity of managing your systems. And it gives you familiar graph technology Gremlin, which is pretty popular in open source world for your transactional OLTP type applications to help out with graph use cases. Where you might need a different solution approach is when you plan to run complex graph analytics, when you want to do machine learning or data science processing on top of your graph OLTP data, when you want to do relationship discovery and resolution on the large graph databases. This is where, and we're going to touch into why this is the case, at least right now. And this is where we recommend, in some cases, to look at the compute engine like Apache Spark, paired with Cosmos Gremlin API to solve those use cases. Now let's look into a little bit of the architecture and why this would be the case. So if you look at the Azure Cosmos Gremlin API on the cover, it is horizontally partitioned graph data. So we do automatic partitioning through hashing of your partition key value, which is one of the properties of your vertices. Edge documents, basically your relationship edges, stored within source vertex documents in the same partition. So basically, every logical partition key will have the vertex and all its edges And each partition is 20 gigabyte in size and has 10,000 request unit throughput capacity. Why we say there is not a good fit for current Gremlin API for analytical queries is because every edge is charged as document as well, and there is RU implications for analytical type queries. In large graph traversals where there is many edges, where you want to do bidirectional traversals or multi-levels walkthroughs with aggregations on top of it, it often becomes expensive. While graph is flexible to be able to do it, but it becomes expensive from compute operation to do aggregation on them. And this is where the Spark is an attractive alternative for scalable compute and memory architecture. To give an example, if this is the simplest graph where Sergey knows Michael, Alexei, and Rick, all right, so we have 4 vertices and 3 edges. To do the simple query, we need 7 RUs because we visit in 4 vertices and 3 edges with the point lookups. But if you pretend that this is Sergey knows now million of people knows that query become million RUs, and if that million becomes, let's say we want to do like a 3-level traversal, you can quickly run into scalability challenges from compute perspective if, let's say, we want to do aggregation at every level. Now, let's look at what are common graph analytical OLAP use cases. So there is, this is not all inclusive, but this is representative sample. There is several scenarios, and the first one is materialized traversals. You often use in fraud detection where you walk the graph and obtain analyzed values for each hop. They're often used in relationship discovery. For example, real-time recommendation engines and document linking analysis, where you scan graph, where you, for example, you don't know about all relationships. You have some relationship in your graph, but you want to discover hidden relationships where, for example, when you do like master data management or trying to link not directly related data with additional type of references, you first want to discover this and create those additional edges with additional properties for querying later. Large complex aggregations, usually in supply chain management, logistics analytics. For example, give me a sum of all properties of all edges connected to this vertex by a certain number of levels. And complex graph computations where like we're doing inventory and network tracking discovery or community management or fraud detection. This is where there is a bunch of graph algorithms like large breadth first, search, large shortest path computation, cycle detections, etc. Ranking, where you actually applying statistical analysis on groups of graphs and edges to produce some ratings and rankings, which you can then either present downstream or update existing properties to be used as additional filters for your traditional OLTP queries. And a lot of times, this goes hand in hand with your OLTP graph, which is still used for serving, but you need to run those analytics once in a while and update the either downstream different systems or update the same graph. If we look at the Gremlin API scenarios, how this all fits together, current Gremlin API is best suited for scenarios that make transactional graph operations traversals, but can adapt to analytical scenarios through the native Apache Spark connectors. So in this picture is Cosmos Gremlin API is in the middle, and we can serve Gremlin OLTP queries through our regular Gremlin API, but we can also serve graph OLAP queries through Apache Spark, whether it's reading graph documents from Cosmos DB, doing that processing, and then it has a choice either write some data back to Gremlin API. Let's say I want to create additional edges based on discovery, or maybe I do the aggregations and I am going to push down to a presentation layer like Power BI reports, where, because a lot of times the actual reporting on graph data, not always in graph format, it often become a tabular format, just like any other reporting. How can we do this? So we can do this because we have a unique capability in Gremlin API where we have different endpoints available. Available for the same data store. So on the back end, Cosmos Gremlin API using the same Cosmos partition storage and represent Gremlin data as GraphSun format, where we store vertices and edges documents based in GraphSun format, and it allows us to represent the same document as a graph, as a vertex or edge to Gremlin API, but we can also query the data using .NET SQL API for SQL API SDK, and you can use them both interchangeably in your application. To illustrate that example, let me show you one thing. This is a simple graph of friends, which is often used in small demos. And if we look at the data itself in Gremlin format, this is a representation of the vertices. We can also query the same data using our SQL API. If we select everything here, we can look at the same data here. So we have the same representation where we have label, we have vertex ID, and then for each property, we have a name and the value represented with a unique ID and some internal Cosmos DB attributes. The edges are represented, if we scroll down to the bottom, edges are represented as well with a label, edge ID, and then we have pairs of sync and vertex properties where we define in the sync. Sync ID is an ID of the vertex where the sync is, sync label, partition, and also the vertex ID, because this is where the edge is stored. And then we have that is edge property true, because that's how we can actually differentiate the edges when we query stuff. Coming back to our presentation, let's now look at Cosmos DB Analytical Store Synapse link, because this is we actually going to leverage in our demo, and this is one of the differentiator for Cosmos DB, where we have transactional data. Let's say this transactional graph, as you do in your CRUD operations, we can represent it for Analytical Store using the autosync, and then that Analytical Store can be using Azure Synapse link to bring is a Spark or SQL query engines to do those analytical operations on top of it and expose it for other downstream use cases. Right now, the Analytical Store is not available for Gremlin API itself from Cosmos DB. It's only available for SQL API and Mongo API, but we can still take advantage of that native integration and Azure Synapse link to avoid the downstream propagation and security key management, et cetera. And this is what we're going to use. Lastly, let's look into Spark part of it, right? So we're saying that Apache Spark is recommended or can be positioned to solve those problems. So how that it works together. So Cosmos Gremlin Spark integration is usually based on open source Spark graph libraries. It's the two common ones are Graph Frames and NetworkX, and our Cosmos Spark connector. So we'll use Spark connector to connect to that SQL API endpoint to be able to read the JSON documents into Spark, and then convert them to Graph Frames and Spark to operate using these Graph Frames and NetworkX within Spark, and then produce the data set at the end to look at the results. We have some examples. I'm referencing some examples here with the links, which will be available in slides later. And historically, this was done using managed Spark clusters like HDI or Databricks. But now, because of that Azure Synapse link, we can now use Synapse Spark pools as well to do this. And this is what we can actually use in our demo. So this is a link to the demo notebook you can use later. But now we're gonna just walk through the process. So this is our Synapse, and the first thing you want to do is basically, if you want to implement it yourself, look at the data set. This is a sample data set you need to load in your Gremlin API database. It represents very simple. It's usually publicly available in many references, representing some people with the first name and the age property. And then we have two type of relationships, friends and followers with a label person, and this is our IDs. I expanded the data set with a few additional people, and I created some additional properties to convert the data set to be more representative for analytical workloads, and I'll illustrate why. And if you want to look at the data set, this is what it looks like if we just execute the query. So it's a little convoluted. It's like a little spider web. So we're gonna use graph frames, Spark to analyze relationships between that data set. And this is a simplistic version of it, but as we're gonna walk through, we can try to project what would it be if this would be a million connections, or let's say it's network operations, or like payments, for example, between people who want to analyze it if there is a fraud ring here for like money laundering, for example. All right, so let's look at our demo. Basically, we have our common small data set. We're describing the several people with property age, and the relationship between those people. I expanded the data set called friends. You probably can find it online. I expanded the data set a little bit to add additional people to kind of like inject it in the network of those friends and followers, and create, and also added additional properties for edges to simulate groups of people to which will discover it, which maybe not naturally observant if you look at the spider web connections, right? So we'll use our graph to discover this. Let me jump to my graph frame. So the way we're going to do it, we're using the graph frames library, which you can add to the data source ADLS, and then load it to Spark using configuration. This is the example. Then you would import your graph frames from that library to use in addition to your Spark SQL function to be able to read Cosmos data using the Cosmos OLTP format. Using that link service, this is where we mentioned Synapse link with Cosmos Gremlin API, using that SQL API endpoint, and the frames would be the name of our graph database. And we'll break that because it's a graph database has both documents for both vertices and edges. We need to split the data frame, all of data frame, into two different data frames. One is vertices, where we filter in by sync as null, and we then subselect an ID of the vertex and then name and age property. And then we also grab in the edges, basically reverse filter where sync is not null, and that's how we split which documents are vertices versus edges. And then we select only 3 properties from the document, because we only need 3 for data frame edges is vertex ID, sync, and label, and we rename them to source destination relationship. Then down the road, this is our data frame, kind of like all our JSON columns. Once we convert it to vertices and edges, it's very nice from visualization standpoint, because it's fairly simple. You have the vertex ID and then name and the value of the property. And then you have the same thing for edges, where you have source destination IDs of your vertices and the label for property name for your relationship, right? So it's friends or followers. Now, next step is we would convert, use our cleansed vertices and edges to create graph frame using the graph frame, and then everything else would be assigned to graph, and everything else will be done based on this graph frame as a source. So now that we converted to graph frame, we can actually do computational, those are simple computational operations where we do count of the total count of all the objects, count of the vertices, count of the edges, combine them to validate that this is the same. We can do some some simple aggregations, like for example, find the youngest user in the graph. We can do vertices group by min age show to show the values. We can count the number of followers in a graph, for example, to query the edges, right? So we can break down graphs, vertices, or edges depending on what operations we're doing with simple SQL-like filters or Spark SQL-like filters. The other interesting thing is what we can use in degrees to do the display of in degrees, and then we can do like additional filters and group by operations on top of it. So for example, this is our representation of in degrees. I remember that when we were discussing the Cosmos DB Gremlin API partitioning, where we store outbound edges within the source vertices, the side effect of this architecture is that inbound traversals are actually expensive because they become cross-partition queries. And if you need to scan a whole graph to calculate the inbound degrees for whole graph, unless it's graph in memory, and this is coming, but it's not available right now yet, this can be a very compute and very heavy operation, and this is allowing you simple computation of this to discover, for example, who is your most connected person. That's very easy to calculate and show. This could be, for example, used for in supply chain when you do route optimization to show, or maybe like when you do airplane flights routing to see what is the most connected airport. Probably Chicago is. I'm from Chicago. Chicago is second most, but it will be in the ballpark. It will be in the top 10 for sure. Now let's look at the other use cases here. Let's look at the community detection algorithm using label propagation. So we're not going to go details in the label propagation, but in a nutshell, what it does, it detects communities of vertices based on their connections, right? So we were shown earlier like the number of connections per vertex, but it doesn't show the groups of people who are connected together. Label allow you to do just this. So this is an example how to run it. We basically define the result variable where we're going to do label propagation on our graph with 5 iterations, right? So we want to do several iterations, like with every machine learning, to get more accurate results. And we're going to run it, and then we're going to just represent the result set with ID, name, and label ordered by label. And label is basically some kind of number generated by the algorithms to group things together. So when we run it, we can actually see that we have a bunch of people who are grouped together, and this is our original group. And then we have my other 3 people in separate categories. They labeled separately because they have different connections to different people. And there is one person who is absolutely different because he doesn't connect to other people. He only connected to this subgroup. And this is actually, you can actually see it here now if we unwind this graph. If we take Samuel here and we move him, let's me first find him, Samuel, right? So if we stretch it, we can see that Samuel only connected to that other group through Samuel Sam, and Samuel Sam are in that separate subgroup, but everyone else is connected together. And that's somewhat the power of that graph analytics to do those type of discoveries. Now, let's look at the other application of the graph algorithm is called PageRank. PageRank is a centrality algorithm using to find importance of connected vertices. Basically, we've kind of like taken that group discovery to next stage where we want to actually, in the big groups, we want to find who is the most valuable person of the group based on the based on the connections. And then there is different variations of this where you can weight edges, like assign different weights, or you can have custom weights assigned, or you can group them with like bias towards arrays of source IDs. So you can do like bias towards one, bias towards multiple arrays. And we can show, so we're gonna, it's actually running still right now, we just restarted it. So the first one is running PageRank with reset probability, and those are kind of like default values. Just full ranking, and then we're gonna do ranking towards person A, who is Alice, I believe, and then the last one was gonna rank towards array of A, B, and C. So we're gonna bias towards 3 people. So it's executing now. So let's see when it's finished. While it's running, I'm gonna quickly walk through the other algorithm at the bottom, where you can also use it to find shortest path algorithm using the shortest path. And in the landmarks, you define the pair of vertices which will be used to define short path. So this is not the short path between A and C. This is short path to from A and C to others, right? So how they connected to others. So it's this should finish. I mean, this is and this is another example why you see that it's even with Spark. Like I'm running with 2 executors with 4 cores each, and it's still taking some time because it's those algorithms are usually compute intensive and probably even in memory. Running it on top of your operational data may not be a good idea because it will take a lot of resources to be able to finish it and may cause, like it could become that noisy neighbor to be able to do it. I think it's, so now it's finished. Now we can display the results. So we're gonna display results one by one. First one was just doing the pure page rank, basically to show who is most influential person in our connections. The Charlie is the most influential. It has a page rank of 3.08, followed by Gab, and then everyone else is um, a lot less influential based on the page ranking, and you can follow the same thing, kind of like have the same understanding based on the graph, because if we find Charlie, so you can see that Charlie has probably the most connections, but everyone else is probably on par, and the second one is Gab. Yeah, that's probably second most connections, and so on and forth. But the other ones who don't have as many connections, or maybe like about the same connections, you can actually still differentiate between them based on the page ranking. The other probably more important thing is when you start looking towards biases, you can actually define that if we bias with specific connection to specific person, now we can actually reset. And it's not just pure number of connections, but there is also a value in connections themselves, depending on the type of edges or other factors within the edges. And then the last one is page ranking with based on the array. So this is where you can actually see the breakdown of the values. So it's personalizing based on the rankings against the other 3. So it's personalized rankings. This is probably could be used in like recommendation engines, where you can do those deep recommendations based on the other connections, which can be sourced in based on the previous results. Scroll down. And the other thing based on the results is also you have the weight of relationships. So that's another thing you can do from the ranking, where it's not just difference on how you rank the vertices. You also can define what type of relationships matter. For example, in our case, friends between like I and B people with those IDs, France has weight 1, but when you have multiple types of relationships, they can actually be different, right? So the D, for example, has different relationships for friend and follow because they have like 2 ones. But when you have many others, you can have different values for weights, and you can use it when you actually use it like in arrays, because now you can assign weight back to relationship as a property and use it as additional filtering choice. And the last thing we want to look at is how to use shortest path algorithm to define the defines how many hops you have between the different vertices. So in that case, we use G to A and C. Basically, we use A and C and evaluate against every other one if there is a connection, right? So we can see that G is connected to C with a 1 hop, C obviously connected to itself, there are 0 hops, and I connected to A with 2 hops and C 3 hops, and so on and so forth. And that's how you can use it. And you can also display it as a path. Basically, if you explode those distances and just use it for pure calculation values, then you can just display the value to make it as a representative, and you can then order by or filter by additional properties. So this is, in a nutshell, all the examples of how you can use GraphFrame library and Spark and Synapse Analytics Cosmos Synapse link to explore Cosmos graph data, online transactional graph data for different analytical use cases, and potentially applies them to your analytical needs from business. And then you have choices: either write the results back to Cosmos DB for additional queries, or potentially present it as a through Spark tables to be available for queries in your presentation layer. So we look at the demo. So now let's do a wrap with 3 takeaways. What we learn and show today is there are differences between transactional OLTP and analytical OLAP graph use cases, and there are different methods to execute them. We explored Azure Cosmos DB and Synapse Link integration, specifically with Gremlin API and Spark, and we looked zoom in a little bit on Spark GraphFrames library and some examples on how to use it to explore graph data in Cosmos Gremlin API for analytical use cases. And hopefully this will spark some ideas how you can leverage your graph data to solving other problems with Synapse Analytics and Spark. So thank you very much for your time, and enjoy the rest of the conference.